Remember when American manufacturing meant muscle, steam, and the unmistakable ring of hammer on steel? Well, those days aren't gone. They've just gotten a whole lot more powerful. What you're watching here is a free forging press from SMS Group, capable of delivering 80 to 100 meganewtons of force. To put that in perspective, that's roughly 18 million pounds of pressure coming down on a single piece of steel. Free forging is different from what you might picture when you think of stamping or molding. The metal isn't completely confined in a die. Instead, massive manipulators rotate and position enormous steel ingots, some weighing over 200 tons, while the press hammers them into shape. It's like a blacksmith's anvil, but scaled up to handle components the size of a locomotive. This particular method is essential for creating large, critical parts, like crankshafts for marine diesel engines and propeller shafts for naval vessels. Back in the 60s and 70s, American shipyards relied heavily on similar equipment. The beauty of free forging is that it refines the grain structure of the steel, making these components incredibly strong and resistant to fatigue. Crucial when you're talking about parts that'll spend decades under tremendous stress at sea or inside nuclear power plants. The SMS Group has perfected this process over generations, combining traditional forging wisdom with computer-controlled precision. Each strike is calculated, each rotation measured. It's a dance between man, machine, and metal, a testament to engineering that bridges the past and present. If you've ever worked a manual mill in your garage or shop, you know the satisfaction of watching a sharp cutter peel away metal like butter. Now imagine that precision amplified 100-fold. The Seiko Tools S564 and JS565 solid carbide end mills you're seeing here represent the cutting edge, literally, of modern machining technology. These aren't your grandfather's cutting tools, though the principle remains the same. Solid carbide end mills are made from tungsten carbide, one of the hardest materials on Earth, second only to diamond. The S564 series features advanced geometries with optimized flute designs that evacuate chips efficiently, preventing buildup that could ruin your workpiece or snap the tool. What makes the JS565 special is its coating, a multi-layer treatment that reduces friction and heat, allowing it to cut through hardened steels that would have been impossible to machine economically 50 years ago. Back then, you'd have to grind these parts, a slow and costly process. Watch how smoothly the cutter removes material in a single pass. The cutting speeds here can exceed 1,000 feet per minute, with feeds that would seem reckless on older equipment. But modern CNC machines, combined with these precision tools, maintain tolerances within 10 thousandths of an inch while doing it. This technology has revolutionized American manufacturing, allowing shops to produce complex aerospace and medical components domestically. It's proof that while the fundamentals of metalworking haven't changed, the tools certainly have, making jobs faster, more accurate, and bringing high-tech manufacturing back home. Here's something you don't see every day: a shovel being born from retired railroad track. There's beautiful symmetry in this. Steel that once carried freight trains across America getting a second life as a tool that'll outlast a dozen conventional shovels. The raw material here is actual railroad rail conforming to Russian standard GOST R51685-2000, though similar American area specifications exist. What makes rail steel special? It's the carbon content, typically between 0.7 and 0.8%. That's considerably higher than mild steel, giving these shovels exceptional hardness and edge retention. Old-timers in the railroad industry will tell you that good rail steel was expected to carry millions of tons of traffic over decades. That same toughness translates beautifully into hand tools. The process starts with cutting sections from recycled rail. Notice how they heat the steel to a cherry red glow, around 1,800 degrees Fahrenheit. At this temperature, the crystalline structure of the steel becomes malleable. The press then forms the basic shovel shape in several progressive strikes, each one refining the contour. This isn't just bending metal, it's forging, which aligns the grain structure and creates a stronger finished product than cutting or stamping ever could. After forming, the shovel blank goes through a controlled cooling process. Too fast and the steel becomes brittle, too slow, and it loses hardness. The metalworkers here have calibrated this perfectly, often using techniques passed down through generations of Russian toolmakers. The final steps include grinding the edge to a precise angle, typically around 20 degrees for digging shovels, and tempering to reduce brittleness while maintaining hardness. Some manufacturers add a wooden or fiberglass handle, but many prefer the traditional all-steel construction with a D-grip. The genius is in the recycling. Using high-carbon rail steel means these shovels weigh less than conventional models while being significantly stronger. It's sustainable manufacturing at its finest, turning industrial waste into premium tools that'll serve another generation of workers. Step into a glass-blowing studio, and you're stepping back in time, yet witnessing a craft that remains fundamentally unchanged for over 2,000 years. What you're watching is pure artistry meeting precise technical skill, and it never gets old. The process begins at the furnace, where glass batch, a carefully formulated mixture of silica sand, soda ash, and limestone, melts at temperatures exceeding 2,000 degrees Fahrenheit. The glowing orange mash you see has the consistency of honey at this temperature. The glass blower dips a hollow steel pipe, called a blowpipe, into this molten glass and gathers a gob onto the end. This is where experience counts. Too little glass and your piece will be too thin. Too much and it becomes unworkable. Notice how the craftsman constantly rotates the pipe. This isn't just showmanship. Gravity is always trying to pull that molten glass downward, and continuous rotation keeps it centered and symmetrical. It's the same principle that keeps a pizza dough round when you spin it. The actual blowing begins with gentle, steady breaths through the pipe, creating a bubble inside the glass gather. Watch how small the initial inflation is. Blow too hard, and you'll create thin spots that'll crack during cooling. The skill lies in maintaining even wall thickness while expanding the form. Between blowing stages, the piece gets reheated in a smaller furnace called a glory hole, necessary because glass cools quickly and becomes rigid. The glass blower uses various hand tools that haven't changed much since Venetian artisans perfected them in the Renaissance. Wooden paddles to flatten, metal jacks to create openings, and shears to trim excess glass. What's remarkable is the timing. The craftsman has perhaps 60 to 90 seconds of working time before the glass becomes too stiff, requiring another trip to the glory hole. Every movement must be deliberate and practiced. This is where decades of experience show, knowing exactly when the glass has the right viscosity for shaping, sensing temperature by color and feel. The finishing process involves carefully transferring the piece from the blowpipe to a pontil rod, allowing work on what was previously attached to the pipe. That final break-off moment is critical. Done wrong, and hours of work shatters. Finally comes annealing, slow, controlled cooling in a special oven over many hours. This relieves internal stresses that would otherwise cause the piece to spontaneously crack. When you need to lift hundreds of tons or secure a drilling platform in a hurricane, you need cable you can trust with lives and livelihoods. Halo Rope's 3-inch steel cables represent engineering that American infrastructure has depended on for over a century. The process starts with individual steel wires, each drawn through progressively smaller dies until reaching the specified diameter, typically around 0.2 inches for this application. These wires undergo heat treatment to achieve tensile strengths exceeding 200,000 pounds per square inch. Watch as the stranding machine winds these wires into strands, typically 6 or 7 wires per strand. The machine rotates at carefully controlled speeds while maintaining precise tension. Each strand then becomes one element of the final cable, wound around a core. usually fiber or an independent wire rope core. The 3-inch diameter you're seeing contains hundreds of individual wires, all working together. The helical pattern isn't just for strength, it provides flexibility, allowing this massive cable to bend around sheaves and drums.